Hey guys, Miss Gill here. We are starting off our year with lesson 1.1. It is on parent functions and transformations. This should feel like a little of a review based on Algebra 1 and a little of geometry. So let's get started. Our learning objectives are listed here. So by the end of this lesson, you should be able to identify the function family, graph transformations of functions, and explain how translations, reflections, stretches, and shrinks affect the graphs of the functions. By now, you should be able to already identify the function family because we worked on the review characteristics and listed out the different types of graphs. So you should be able to say you can do that part, and then we're going to now work on the next. So let's dive into vocabulary because speaking correctly about math is a great thing to be able to do. All right, so we're just going to go ahead and get all the vocabulary out. Functions that belong to the same family share key characteristics. The parent function is the most basic function in a family. Functions in the same family are transformations of their parent function. So a translation changes let me back up. This is my first lesson, so bear with me. It's okay. A transformation changes the size, shape, position, or orientation of a graph. A translation is a transformation that shifts a graph horizontally and or vertically but does not change its size. Now, I do want to point out that it is described as shifting. So if you see something that says it's shifting, it is a translation. However, if I'm talking to you about this or you're describing the transformation to me, I do want you to use the word translation. So in your answers and in class, I would prefer for you to say translation over shifting or moving. A reflection is a transformation that flips a graph over the line called line of reflection. A reflected point is the same distance from the line of reflection as the original point, but on the opposite side of the line. So some of these should be familiar from geometry. And so we're just going to look at how they relate to different types of graphs. We will talk about stretching and shrinking later in this lesson. All right, so identifying a family function. So based on what we talked about with the reviewing characteristics paper, you should already be able to look at this. You have two things that tells you what type of graph this is. One, the shape. So this has a V shape. Also, notice in the equation we have absolute value bars. So we know right away then this is an absolute value function. So our directions do say it's important to read them all. Compare the graph of f to the parent function. So we know that the parent function starts at the origin, and then it really just kind of goes through the corner of all the boxes. Sorry, trying to make it look not too bad. So this is f of x equals the absolute value of x. So we are just comparing this one to this one. So we can see that it has shifted up, so we would say it's been translated 1 unit up. Now this blue graph compared to my red graph does look a little skinnier. Now we haven't really talked about that yet, but that skinnier, if you remember from geometry or from Algebra 1, that is called a stretching. So the graph appears to be translated up. Right now I would be good with just that because we will talk about how to look at the equation and tell what's going on too. But in this case, we would say that the graph to compare them, it seems to be translated and it seems to be stretched. Since we haven't really talked about stretching or shrinking yet, I decided to just use the word it appears or it looks skinnier. Okay, so it moved up, it looks a little skinnier. And guys, I just don't want to make you watch me write all the words, so that's why I pause it to write the words. You can do the same as needed. All right, so graph g of x equals x minus 4, then compare it to the parent function. So they have the parent function already. All right, the way that we could graph x minus 4 without knowing our transformations just yet is, remember I told you in class that you can choose any x value, plug it in, and you get a y value. So for example, if I made an x and a y table and I just picked some values, so I do want some negative values because I want my graph in the negative section. All right, so let's do -2, -1, 0, and I have room for 1. And so all we're going to do is we're going to substitute in those values for x and get our y. So we have -2, so -2 minus 4 gives us -6. Now we're going to plug in -1. -1 minus 4 gives us -5. Substitute in 0. 0 minus 4 gives us -4. And then substitute in 1. 1 minus 4 gives us -3. So I'm going to plot those points on my graph. So we got -2, -6, -1, -5, 0, -4. And notice you really could have just did 2 of these, and you would have seen that they're going through the corner of all of the boxes. I'm going to do my best to make this straight. All right, so this is g of x. So we're comparing g of x to f of x. So what does it look like happened? Well, we started here, now we're down here. So we would say that it appears to have translated down. Now, eventually we will get to where we're talking about how much is it translated down. If you wanted to go ahead and start putting that in there, you could by comparing. So we got 1, 2, 3, 4. So it was translated down 4 units. But for now, we're just trying to refresh our brains and make it not too challenging. All right, graphing and describing reflections. So we are going to graph p of x is equal to -x squared, then compare it to the parent function. Well, we have x squared here. So what happens if we make it a negative? We're just reflecting it. It's even telling us that we're going to reflect it. So just for time purposes, and because nothing else is happening, it's not translating, it's not stretching or shrinking, we're simply taking this graph and flipping it over since there is nothing else but just that negative. And if you want to do like we did in the previous one and plot some points, you would notice that we would get these same points. So remember, reflection is the same distance away from the line of reflection. So all I did was say, oh, these are 1, so that's 1. These are 4, so that's 4. And so now I'm going to draw a line. And voila. All right, so now we need to compare it to the parent function. So this one, it's the same graph, it just flipped over the line, but we're not going to use the word flip. We're going to use our math words and say it was reflected over, and because it was flipped over this way, we're going to say over the x-axis. So it was reflected over the x-axis. All right, we're halfway there. Moving along. Next page. All right, so now we're going to talk about the stretching and the shrinking. I put some study tips right here to visualize. So when you're talking about stretching, think of like a rubber band. When you pull a rubber band up and down, like it makes it skinnier, it pulls it tighter. And then if you visualize like pushing on a ball of slime, the more you push it towards the table, the fatter it's going to get, or in this case, the wider it would get. So just kind of something to visualize with it. All right, so another way to transform the graph of a function is to multiply all of the y coordinates by the same positive factor. I do want to point out this is an important word because as you noticed earlier we had a negative. That negative is a reflection. So every time we stretch and shrink, it will always be a positive number. If you have a negative, that is affecting the reflection part of it. All right, so when the factor is greater than 1, so when your factor is greater than 1, the transformation is a vertical stretch. Vertical stretch. So right now we're just talking about vertical stretches and shrinks. We'll talk about horizontal ones in a later lesson. When the factor is greater than 0 but less than 1, not to be confused with a fraction because the fraction 3/2 is greater than 1. So just keep that in mind as you go through these lessons. So when the factor is greater than 0 and less than 1, it is a vertical shrink. So what are these factors Ms. Gill is talking about? Well, remember we're multiplying. So if you have something being multiplied to your parent function, it is going to either stretch it or shrink it depending on which one of these categories it falls into. So for example, if we look at this one, it gives us the parent function. We see that it's being multiplied by 2. So what does that tell us? That tells us that it's going to fall into this category and it's going to be a vertical stretch. And a vertical stretch will appear to be skinnier. Let's make a note of that just so you have it. So a vertical stretch appears to be skinnier. A vertical shrink appears to be wider. All right, so how can we do this? Well, we're going to take our numbers just like we did earlier. Let's make a quick T-chart. And we're going to plug in some x values and get some y. I want to stay right here. So they use -2, -1, 0. I'm using those same ones. And we are simply going to take those values and plug it in. So -2, if I was to find the absolute value of -2, that gives me +2. Remember, absolute value, your answer is always positive. It's simply the distance from 0. So the absolute value of -2 is +2. 2 times 2 is 4. All right, absolute value of -1 is +1. 1 times 2 is 2. And if I'm going too fast on this part, remember we do get to use technology and we will find quicker ways in the future to do this. So if you want to talk about this more, we can. If you feel like, because I've always had students say, Ms. Gill, I don't know where you're getting those numbers from. I'm just making up the x values, plugging them in to get the y values. All right, so if I plug in 0, absolute value of 0 is 0. Anything times 0 is 0. Plug in 1, I get the absolute value of 1 is 1. 1 times 2 is 2. And last one, absolute value of 2 is 2. 2 times 2 is 4. So I'm going to plot those points. So I have a -2, +4, -1, +2, 0, 0, 1, 2, and 2, 4. And then I'm going to do my best to draw this line as straight as possible. And so now I have g of x. All right, notice I'm writing this because this labels this graph. They have this one as f of x. This is the graph of g of x. And so does my graph appear to be skinnier? It sure does. So knowing that will help you identify a graph without having to do all of this. All right, moving on. We're almost there. All right, now we have 1/2 x squared. So if we go up here, when the factor is greater than 0 and less than 1, it's a vertical shrink. A vertical shrink appears to be wider. So this part of our graph should get closer to the x-axis. So again, just going to make a quick little T-chart over here. And let's plug in the numbers they used before. So we got -2, -1, 0, 1, 2. All right. So we have x squared. So we're plugging this in. So -2 squared gives me 4. Half of 4 is 2. All right, -1 squared gives me 1. Half of 1 is a half. Anytime I plug in 0 and I multiply, I'm going to get 0. All right, 1 squared is 1. Half of 1 is a half. I'm just mentally plugging in. I plug in 2 for x. I get 2 squared is 4. A half of 4 is 2. And now I'm going to plot those points. And this is h of x. So notice it does appear to be wider. It's not drastically wider. It's just slightly wider. All right, so just some ideas. So it does say compare. We did forget that part. So if you will make a note that the graph stretches because it appears to be skinnier, the graph shrinks because it appears to be wider. All right, so g of x stretches because it appears to be skinnier, h of x shrinks because it appears to get wider. So example 5 does tell us that we can use technology. Unfortunately, I am making this first video at home and I forgot to bring a graphing calculator. So what I will do is in class, we are going to practice the graphing calculators and fill this part out together on Friday. So hopefully you have watched this video before Friday. If not, and you were in class on Friday, then we've already done this part. All right, so we're skipping this for now, but we will do it together in class. So I made a note to do together in class. So when you come into class on Friday, if you watch this video before Friday, come in, grab a graphing calculator. That way we can practice putting this in together. Okay. All right, last one. I know we don't love word problems, but it's okay. I tried to break them down as easy as possible for you. And this isn't a bad word problem. All right, it says that the table shows the height of a dirt bike x seconds after jumping off a ramp. What type of function can you use to model the data? And then they want us to estimate the height after 1.75 seconds. So if you can imagine somebody on a dirt bike, right, and they're jumping, it would make a U shape, like an upside down U shape, which by now we should know is a quadratic formula. So what type of function could you use to model the data? A quadratic, did I say formula? A quadratic function. So if I said formula, sorry. Quadratic function. Yes, in a later chapter, y'all will have to do the quadratic formula, but it's okay. I'll teach you the song and have the formula written out for you. So, all right, so we've got that part. Now we need to estimate the height after 1.75 seconds. So this is going to be my height. And so if that's my height, that means that this has to be my time in seconds. So because I make mistakes, I'm going to use a pencil for this part. And we got 0, we got a half, we have a whole, we got a 1.5, we got 2 wholes, and just for funsies, let's go to 3. All right, so now our height, we're ranging anywhere from 8 to 24. So let's go as high as 25, and we can count by 5s. So we have 5, 10, 15, 20. Okay, that looks great. All right, so at 0 seconds, he starts off at a height of around 8. So we're going to say right there. At a half of a second, he is up to 20. Right, that's a half, yes. Okay, at 1 second, he has gotten at his highest point of 24, which is almost 25-ish. And then he's coming back down. So at 1.5, he's right there. And at 2 seconds, he's back to 8. So if we draw and connect the dots, we see that it does make a parabola. So what would happen here? This is when he hits the ground, I guess, because it doesn't really say, does it say, oh, he did jump off a ramp. So this would be like the ground. All right, so we would say after about somewhere between 2 and 2.5 seconds, he landed it. They want us to estimate after 1.75. Of course, why not? So 1.75 would be somewhere in here. So let's just do our best to follow up. Again, we are estimating. So as long as you are in the ballpark of this figure, there's no wrong answers. So we got 5, 10. This would be 15. So maybe like 13 or 14. So we could say 13 or 14-ish, right? Yeah, looks good to me. Right, we got 5, 10. Oh, nope, hold on. Oh, that was 8. So yeah, 5, 10, and that would be 15. So I'm going with 13. So we would say estimate the height. The height is about 13 feet after 1.75. If you like 14, we're estimating. So if you like 14 better, go for it. All right, so that is the end of the lesson. Again, we are going to do example 5 together in class so I can show you how to do this on your graphing calculator. And then you will work on your practice that goes with this. If you have any questions, anything tripped you up on this at any point, make a note to ask me. Again, don't stress too much about the T-charts. If you want to practice a couple of those, we can. Just let me know. So I will help you with whatever questions you have. Hopefully you found this lesson somewhat easy. They won't all be this easy, but it's the first lesson. Don't want to scare you too much. All right, guys, so that is the end of lesson 1.1. I will see you in class.